3x cube plus 2x square plus 4x minus 1 by gx equals to x square minus 2x plus 3 in the ring Z5x. So you need to call the division algorithm in Z5x. Okay. So by using division algorithm, what we shall get? That is x square minus 2x plus 3. It is x to the power 4 minus 2x square plus 1. So we shall follow the normal division process, what we have done earlier. That is, we must put x square. Then what will happen? This is x to the power 4 minus 2x cube plus 3x square, right? Now, so this will be minus x cube minus x square plus 4x. Now we can put minus x, that is minus x cube plus 2x square minus 3x. So again we have, so this is minus 3x square plus 2x minus 1. Now it is minus 3, then minus 3x square plus x plus, what is this? This is 3 into 2, that is 6. But we are in the field Z5. So it must be x. বোঝা গেল?
So 2x কি করে আসছে?
এই দেখো 3 into 2 it is 6. Now we are in Z5, 5 modulo. তাহলে 6 equivalent to 1.
আচ্ছা।
So that is why we put here x, and it is minus 4 again. That is 3 into 3 is 9. Now modulo 5 is 4, so it is minus 4. So plus minus plus. So that is, it is x, and this will be plus 3. So this gives us, so this gives us x to the power 4 minus 3x cube plus 2x square plus 4x minus 1 is equal to x square minus 2x plus 3, x square minus x minus 3 plus, where qx is x square minus x minus 3, rx is x plus 3. Okay, so we have got the quotient and remainder. ঠিক আছে, তাহলে আমরা যে কোনো একটা এরকম রিং এর উপর ডিভিশন অ্যালগরিদম অ্যাপ্লাই করতে পারি। ওকে, আরেকটা প্রবলেম করো দেখি নিজেরা। প্রবলেম, যে show that 1 is a zero of the polynomial x to the power 4 plus 3x cube plus 2x plus 4 belongs to Z5x, and factorize it, and factorize this polynomial, it in Z5x. এটা একটু করো তো দেখি নিজেরা। একটু খাতা নিয়ে করো। হ্যালো হ্যালো, শোনা যাচ্ছে? ওকে, so exercise. Now note that we have already used the synthetic division process in classical algebra, right? That is in the ring Z plus dot. But at the same time, we can also use this technique of synthetic division in any polynomial ring over a field. Okay. So note that one can use the technique of synthetic division as well. Okay. Now we move on to define what does it mean by an irreducible polynomial over a field F. That is a non-constant polynomial fx belongs to this capital Fx is defined to be an irreducible polynomial over F if Fx cannot be factored into Fx cannot be factored into Gx Hx. Fx cannot be factored into Gx Fx of two polynomials Gx and Fx in capital Fx where degree of Gx, degree of Hx is strictly less than the degree of Fx. That is, we cannot factor Fx into two polynomials having lesser degree, lower degree than Fx. So this type of polynomials are called irreducible polynomial over the field F. This one. We must mention the field each time because this is crucial. Okay. And it should be noted that so we must note down that we should talk of the concept of irreducibility over a field F. So we should mention that field, that is over a field F, not just not just the concept of irreducibility. That is, we must mention that is, it is irreducible over a field F. So the field should be mentioned. Irreducibility. Okay. For example, x square minus 2 is irreducible over the field Q, but it is reducible over the field of reals, right? So mentioning this field is important. Over which field it is irreducible. So that is important. Also, it is to be noted that a polynomial fx may be irreducible over the field F, but it may not be irreducible if it is viewed over a larger field, E containing that field F, containing F, which is the case we have already talked in the previous example. That is, Q is a subfield of R. So x square minus 2 is irreducible over Q, but it is not irreducible over R. Okay. This should be not also. Okay. So it is. Okay. Now one can observe that. The units in fx. What are the units in a polynomial ring? Units means the non-zero elements which has multiplicative inverse.
divisor.
Right? No. Multiplicative inverse. Unit means a non-zero element which has multiplicative inverse. Right? Now, okay. So what are the units in fx? These are precisely the non-zero elements non-zero elements of the field F. So the units in Fx are precisely the non-zero elements of the field F. And this will influence us. This will influence us to define what? To define that a non-constant polynomial, small fx in capital Fx is said to be irreducible over F if in any factorization, that is, if you can factorize this Fx. So if in any factorization of Fx, that is, if we can express Fx as the product of a gx and hx in Fx, then what will happen? What is our conclusion? Then either gx or hx must be a unit. That is a constant. That is, if it is possible, if it would possible to express Fx as the product of two polynomials gx and hx in capital Fx, then either gx or hx will be a constant in the field. So that is the way you can view irreducibility of a polynomial Fx over the field capital F also. Now example, so consider a polynomial Fx equals to x cube plus 3x plus 2 in the ring Z5x. Then one can check that. Now if we put each element of Z5 to x, evaluate this polynomial, then what we shall get? That is, if we put 0 class, if we evaluate this polynomial at 0, then this is 0 class cube to 3 0 class plus 2 class. That is, it must be 2 class, which is not equal to 0 class. Now if we put F1 class, then it is 1 class plus 3 1 class plus 2 class, that is 3 plus 2 plus 1, that is 6 class, which is equivalent to 1 class, which is again not equal to 0 class. So in this way we can verify the irreducibility of Fx for each member of Z5, and we find that Fx not equal to 0 for all x belongs to Z5. That is, there exists no such x belongs to Z5 for which Fx equals to 0. So this in turn shows that this fx is irreducible over Z5. That is, fx has no 0 in Z5. So that is why it is irreducible. And this way of testing irreducibility, now this way of, so the test of irreducibility by finding zeros. So this way of testing irreducibility by finding zeros will work good for quadratic cubic polynomials over a finite field. That is, if you are considering a finite field, then, and also if you are considering the degree of the polynomials is 2, 3, maybe some 4 degree polynomials sometimes, right, over a finite field having a small number of members. That is, if we consider a finite field having 1000 elements, then it would be very much complicated to check for each element, right? So this way of testing irreducibility by finding zeros will work good for quadratic, cubic, and sometimes quadratic, quadratic polynomials over quadratic, cubic, biquadratic, sometimes over a finite field having a small number of zeros. But it will not work. It will not work for large fields. So that is why we need to, have some criteria. We need to have some criteria at our hand to determine irreducibility. Of polynomials. In fx. So you need to have some criteria which will help us to determine the irreducibility of polynomials in the polynomial ring fx over a field f. So the first criteria is the next theorem. That is, if we consider a polynomial fx belongs to capital Fx having degree 2 or 3, then fx is irreducible over f. Then fx is reducible over f if and only if it has a 0 in capital F. So if we consider a polynomial fx having degree 2 or 3, then fx is reducible over f if and only if it has a 0 in f. Okay. The proof is as follows. Suppose that fx is reducible. That is, fx can be written as expressed as a gx hx over f, where degree of gx, degree of hx must be strictly less than degree of fx. Now since degree of fx is, by assumption, it is either 2 or 3. So either of the, degree of either of the polynomials, gx or hx, their degree must be degree 1, right? Sorry, that is degree of one of the polynomials. Degree of one of the polynomials, gx or hx, must be of degree 1. Say, let us suppose that gx is of degree 1. Now since degree of gx is 1, so gx takes the form gx equals to some alpha x plus beta, right, in fx, where this alpha is not equal to 0, where this alpha is not equal to 0, and therefore g of minus alpha inverse beta. So if we evaluate gx at minus alpha inverse beta, what will we get? It's going to be 0, right? That is alpha. If we calculate alpha minus alpha inverse beta plus beta, so that is minus beta plus beta, that is 0. Okay, so G has a, which shows that Gx has a 0 in F. Gx has a 0 in F, and therefore this is a 0 of fx2, fx in f2, right? The 0 of gx is a 0 of fx, that is, if we put minus alpha inverse beta here, so fx will be 0. So zeros of gx are zeros of fx. Okay, it is fine. ঠিক আছে তো? Now if we consider the converse part, then it is very much trivial. That is, conversely, if we suppose that fx has a 0 in f, say alpha belongs to f, then since alpha is a 0, so then by division algorithm one can say that then we have that the polynomial x minus alpha is a factor of fx in capital Fx, which implies that fx will be represented as some x minus alpha into gx for some gx belongs to fx. So hence fx is reducible. So hence fx is reducible over f. Yes. So in case of the polynomials having degree 2 or 3, we need to find out the zeros of that polynomial in the field f. Okay. Now the next theorem is in the ring of polynomials over the integral domain Z. So what is it? If fx belongs to zx, that is fx is a polynomial with integer coefficients, then fx factors into a product of two polynomials. If fx then fx factors into a product of two polynomials of lower degrees R S in Qx if and only if it has such a factorization. It has such a factorization with polynomials of the same degrees Rs, but with coefficients in Z. That is, if we can factor fx into two polynomials of lower degrees Rs in Qx, that is over the field of rationals, then if and only if it has a factorization with polynomials of the same degrees, the degrees will be same, but having coefficients over the domain of integers. So let us prove this theorem. So let fx belongs to zx be factored into two polynomials. Let fx belongs to zx be factored into two polynomials of lower degree. Let fx belongs to zx be factored into two polynomials of lower degree in the ring Qx. That is, we factor this fx over the field of rationals. That is, fx can be represented as product of gx hx, where degree of gx is r, degree of hx is s, and we suppose that degree of fx is n. such that 0 less than r comma s is less than n, and gx fx both are in the ring Qx. That is, their coefficients are rationals. So since gx hx belongs to Qx, so their coefficients must be of the form so their coefficients must be of the form p by q. Okay. Now what we shall do? We adjust by adjusting the denominators. That is, suppose the polynomial looks like this: 2 by 3x plus 1 by 4. Then what we shall do? We can make it plus 8x plus 3 by 12. Right? ঠিক আছে? 12x square plus 8x plus 3. Or actually it is equal to 1 by 4, 4x square. Oh no, sorry. So this is what we shall do. That is, we are adjusting the denominators. We will get that. So we shall get that. We will get that some c into fx g1x into h1x, where this c belongs to z, and of course c not equal to 0. That is, here the c is 12. Okay. Right? And the g1x and h1x both will be a polynomial over the domain of integers zx. And check that the degree of this polynomial is 2, and also the degree of this polynomial is also 2. That is, the degrees will be same. Right? So where the degree of g1x is r, degree of h1x is s. Okay. Now by taking out the coefficients, by taking out the coefficients, if possible, of course, coefficients d, d1, d2 belongs to z, such that fx will be written as dgx, g1x will be written as d1 g1x, d1 g2x, and h1x will be written as d2 h2x. 2x. And this will give us that GCD of the coefficients, GCD of the coefficients of gx, g2x, h2x are exactly 1. That is, there is no other common factors in the coefficients of gx, g2x and h2x. Okay. So hence C fx is g1x, h1x, and this implies, so we put fx equal to dgx, so it is c dgx equal to d1 d2 g2x h2x, where g2x h2x belongs to z with GCD of coefficients GCDs of the coefficients of G2x, H2x are exactly 1. So hence this implies, so what we shall get? What will happen now? That CD, that is D1, D2 equals to plus minus CD and no other options. Okay? Hello? And this gives us CDGX equals to plus minus CD G2X H2X. That is to say, Fx equal to dgx implies plus minus d g2x, and the converse part is trivially true. The converse part is trivially true because every integer is a rational, right? Every integer is a rational. ঠিক আছে? শুনতে পাচ্ছি না কিছু। হ্যালো? Okay. So therefore, we can prove an immediate corollary that if we consider a polynomial fx is whose leading coefficient is 1, n minus 1 x to the power n minus 1, n minus 2 x to the power n minus 2, a1x plus a0 belongs to zx with a0 not equal to 0. Then if fx has a degree, if fx has a 0 in Q, then it has a 0, if fx has a 0 in Q, then it has a 0 k belongs to Z such that k divides a 0. That is, if we can find out a 0 of fx in the field of rationals, then it must have an integer, must have a 0 in the domain of integers, having the property that that 0 will divide the constant coefficient. So this is important, and this will give you some clue that what the zeros may be. Okay. The proof is obvious, since let us suppose that fx has a 0, x0 belongs to Q, and so it has a linear factor x minus x0 belongs to Qx. So let us suppose that fx has a 0, x0 belongs to Q, and so it has a linear factor x minus x0 belongs to Qx. Then fx must have a factorization, with a linear factor in Zx, and so there exists an integer k. So fx must have a factorization with a linear factor in Zx by the above theorem, and so there exists an integer k such that fx will be represented as the product of x minus k and a polynomial of degree n minus 1, of degree at most n minus 1, such that the last coefficient constant term, that should be a0 by k. Where this a0 by k must be an integer, which in turn says that k divides a0. Okay. So thus we have proved that if fx has a 0 with fx with leading coefficient 1 and with constant term with non-zero constant term a0, and if fx has a 0 in Q, then it must have a 0 k such that k divides the constant term a0. And this indicates that remark that we have noticed that if a polynomial fx belongs to Zx, if a polynomial fx belongs to Zx with leading coefficient 1, having non-zero constant term, a0, so if a polynomial this with leading coefficient 1 having non-zero constant term a0 has a 0 in Q, then it must have a 0 in Z which divides a0, which divides a0, that is the possible integers, that is the possible integers that will be the zeros of the polynomial over Z are those which are divisors of the constant term. Constant coefficient A0. Okay, so we need to check what are the divisors of A0. So that we must check. That is, let us, for example, let us have some example. That is, if we consider simply x square minus 2 belongs to Qx, and which has been proved already, to be irreducible over Q. It has already been checked that it is irreducible. Now if we want to check, if we want to prove this one in terms of this corollary, then let us suppose that forcefully that let it has a 0. Let it has a 0 in Q. Then by the above corollary, it must have a 0 in Z. It must have a 0 in Z, which will divide the constant coefficient, which will divide the constant coefficient, constant coefficient minus 2. And this indicates that the only divisors of 2 are plus minus 1 plus minus 2, and this indicates that the possible zeros of x square minus 2 over Z are plus minus 1 plus minus 2. But one can check that if one can check that plus minus 1 plus minus 2 are not at all a 0 of x square minus 2 in Z. For if we put plus minus 1, then what will happen? Plus minus 1 square minus 2 is 1 minus 2, that is minus 1, which is not equal to 0, and plus minus 2 square minus 2 is, so this is 4 minus 2, so this is 2, which is again not equal to 0. So this way we can also prove that x square minus 2 is irreducible over q. So this is another kind of proof. Now problem, just do it on your own. That if we consider fx is x to the power 4 minus 2x square plus 8x plus 1 over qx. Show that fx is irreducible. ঠিক আছে, ওকে, আজকে এই পর্যন্ত থাক। এই প্রবলেমটা করো, আরো কিছু প্রবলেম পাঠাচ্ছি। ওকে, হ্যালো হ্যালো
Okay.